Welcome to Chapter 9, Factoring, a Key Skill in Math. Let's start exploring this captivating subject. Factoring simplifies polynomials into easier components, making them easier to work with and solve. It involves breaking down expressions into products of smaller expressions, facilitating the manipulation and solution of algebraic equations. This technique is essential for tackling complex algebra problems. Common factor factoring. This approach identifies and extracts the greatest common factor, GCF, from all terms of a polynomial. For example, with the polynomial 6x to 9x, the GCF is 3x, which when factored out results in 3x to x3, thus simplifying the polynomial for further operations. Factoring by grouping. This is used for polynomials with 4 or more terms. It involves grouping the terms into pairs and extracting the GCF from each pair. For instance, with the polynomial 2x3 4x2 3x6, grouping and factoring lead to 2x3 4x2 and 3x6. Factoring out the GCFs results into x2, x2 3, x2, and removing the common factor, x2, simplifies it to x2 to x2 3. Factoring quadratic expressions. This process applies to expressions like x to bxc. Methods such as the quadratic formula, completing the square, or trial and error are used. For example, for x to 5x6, identifying two numbers that multiply to 6 and add up to 5, which are 2 and 3, leads to the factored form x2, x3. Difference of squares. This method is used when a polynomial represents the difference between two perfect squares. For example, x to 9 factors into x3, x3. Sum or difference of cubes. For expressions like a 3b3 or a 3b3, specific formulas are used to factor them. For instance, x3 8 is factored as x2, x2 to x4. Using these methods, factoring is a crucial skill in algebra, helpful in solving equations, simplifying expressions, and finding roots of polynomials. Let's begin to thoroughly explain the concepts for each of them in detail. Let's explore how to find the greatest common factor, or GCF, in a polynomial. Consider the polynomial 6x to 9x. Here, the GCF is 3x. By extracting 3x from the polynomial, we simplify it to 3x to x3. This step shows how the polynomial is neatly factored by pulling out the common factor from all the terms. In this lesson, we will explore a straightforward explanation of factoring. Let's begin by identifying and extracting the greatest common factor GCF through clear examples. Example 1. We are given the polynomial 6x2 plus 9x. Step 1. Find the GCF of the terms. For 6x2 and 9x, the GCF is 3x. Step 2. Factor out the GCF from each term. Hence, 6x2 breaks down to 3x to x, and 9x becomes 3x3. Step 3. Combine the factored expression. Therefore, 6x2 plus 9x can be simplified to 3x, 2x plus 3. Example 2. Factor the polynomial 1 to x3, 8x to 4x. Step 1. Determine the greatest common factor, GCF, for the terms. The GCF for the terms 1 to x3, 8x2, and 4x is 4x. Step 2. Extract the GCF from each term. Dividing 1 to x3 by 4x results in 3x2. Dividing 8x2 by 4x results in 2x. Dividing 4x by 4x results in 1. Thus, the terms break down as follows. 1 to x3 is 4x times 3x2. 8x2 is 4x times 2x. 4x is 4x times 1. Step 3. Compose the factored expression. By extracting the GCF, 4x, from each term, we rewrite the polynomial as 1 to x3, 8x to 4x equals 4x times 3x2 to x1. Hence, the polynomial 1 to x3, 8x to 4x can be rewritten as 4x, 3x2 to x1. This reveals the common factor clearly and simplifies the expression. The examples demonstrate the process of factoring polynomials by identifying and extracting the greatest common factor. This technique streamlines the expressions, making them more straightforward and manageable. Let's explore factoring by grouping, a technique for polynomials with 4 or more terms. Start by dividing the terms into pairs. For each pair, extract the common factor. Then spot any shared factor across these pairs. For instance, take 2x3 4x2, 3x6. Group it as 2x3 4x2 and 3x6. From each, factor out the common elements to get to x2, x2, and 3x2. The last step is combining these results using the shared factor here, x2, leading to x2 to x to 3. Let's delve into factoring the polynomial to x3 plus 3x2, 4x6, starting with a structured approach to simplify it. First, we split the polynomial into two parts, the first with the terms 2x3 plus 3x2, and the second with minus 4x6. This division sets the stage for easier factoring. Next, we identify and extract the greatest common factor, GCF, from each part. From the first part, 2x3 plus 3x2, extracting x2 gives us x2, 2x plus 3. From the second part, minus 4x6, extracting to gives us 2x plus 3. Note that 2x plus 3 appears in both parts. This is crucial, as it allows us to pull 2x plus 3 out from the entire expression, simplifying it to 2x plus 3, x2, 2. Therefore, the polynomial 2x3 plus 3x2, 4x6, is broken down into 2x plus 3, x2, 2. This example illustrates the steps of dividing the terms, extracting the GCF from each segment, and isolating the common factor. The method of grouping and factoring is an effective way to simplify complex polynomials, making them easier to handle and further work with. Understanding how to factor quadratic expressions, let's look at quadratic expressions like x to bxc. There are a few common ways to factor these, such as the quadratic formula, completing the square, and trial and error. For example, take x to 5x6. To factor it, find two numbers that multiply to 6 and add up to 5. Here those numbers are 2 and 3. Thus, we can write the expression as x2, x3, which helps see the solutions more clearly. Let's explore how to factor the quadratic expression x to 5x6. The aim of factoring is to simplify the expression into a product of simpler expressions. We start by looking for the numbers whose product equals the constant term, 6 in this case, and whose sum equals the middle coefficient, 5 in this case. We find that the numbers 2 and 3 work, as to asterisk 3 equals 6 and to plus 3 equals 5. This allows us to rewrite the quadratic expression x to 5x6 as x2, x3. The expression x2, x3 is easier to evaluate for specific values of x and makes further algebraic operations more straightforward. The concept known as difference of squares helps in algebra, especially with polynomials that show a difference between two squared numbers. Take the expression x to 9, for example. In simpler terms, it's x squared minus 9. By applying the difference of squares, we can factor it into x3, turning the complex polynomial into an easier product of two binomials. Let's simplify the expression 16y2, 25. This is the difference between two perfect squares. We can write it as 16y2, 25 equals 4y2, 5, 2. Using the difference of squares formula, which is a2, b2 equals a plus b, ab, we apply it here. By substituting our values, we find 16y squared minus 25 equals the product of 4y plus 5 and 4y minus 5. Thus, the expression factors to 4y, 5, 4y plus 5. Now, let's explore expressions like a cubed plus b cubed or a cubed minus b cubed. Take x cubed plus 8 as an instance. This can be factored into x plus 2 times x squared minus 2x plus 4, which helps simplify and clarify the parts of the equation. Example 1. Simplifying the expression. we begin by addressing the algebraic expression x3 plus 8x3 plus 8. Our goal is to identify and merge similar terms, simplifying the equation to its simplest form. The formula for the sum of cubes is a3 plus b3 equals a plus b, a2 ab plus b2. Here, by setting x as a and 2 as b, we reformulate the equation to x cubed plus 8 equals x plus 2 times x squared minus 2x plus 4. This gives us the factored form of the polynomial x3 plus 8, described as x plus 2, x2, 2x plus 4.